Welcome back to Math 103. This is video number 7 on growth and finance. We're looking at this problem about successive increases and decreases in the Dow Jones Industrial Average. The temptation here that we want to avoid, the temptation is to think, 3% plus 4% is 7% worth of increases, contrasted with 5% plus 2% equals 7% of decreases. Well, 7% of increases versus 7% of decreases, those must cancel each other out, and we just end up right back at 18,000. But that would be mistaken, because these increases are one after the next. Increases or decreases are one after the next. This 5% decrease is not 5% of 18,000, it's 5% of whatever the level is at the end of the first week. And this 4% increase is not 4% of 18,000, it's 4% of wherever the Dow is at the end of the second week. So these four different percentages are not percentages of 18,000, they're not percentages of the same thing, so they're apples and oranges if we try to add them to one another. We instead have to think in terms of a growth factor for this growth, a decline factor for that decline, a growth factor for this growth, a decline factor for that decline. Those factors all have to be multiplied together. We find that the overall growth-decline factor, turns out to be a decline, is 0.9973 for the entire 4-week period, so we can go back and answer our question. The new value will be 18,000 times 0.9973, which turns out to be 17,951. Traditionally, this value of the stock index is rounded to the nearest integer. Notice how the overall effect was not to remain steady at 18,000, or not to come back at the end to 18,000. The overall effect of these 4 weeks of growth and decline was a decline, a net decline. We would have gotten that wrong if we had added and subtracted percentages instead of multiplying growth factors. To answer the question about what percentage change has taken place, we can look at this decline factor. We could convert it to a percentage, 99.73%, and compute 100% minus 99.73%, right? Because it's 99.73% of the original value which still remains, so the difference between 100% and 99.73% will be the percentage lost. Or we can argue, it's good to come back and look at this viewpoint again, any growth or decline factor can be written as 1 plus something, that is 1 plus the change. So how much change took place? Well, I subtract 1 from both sides of the equation and find that in decimal form, the change is negative 0.0027. In other words, there's been a decline of 0.0027 in decimal terms. As a percent, that's a decline of 0.27%. It's important to understand that every example of financial growth can be reformulated as an example of population growth, and that is because the same mathematics describes both situations. For example, if the world population increases by 1.2% each year, we can ask, what is the overall 50-year growth factor? And by what percentage will the world population have increased after 50 years of such growth? We could also ask if the world population decreases by 1.2% each year. What is the overall 50-year decline factor? And by what percentage will the world population have decreased after 50 years? The overall 50-year growth factor will be 1.012 raised to the 50th power. Where did that come from? That's 1 plus the annual growth rate put into decimal form. So this is 1 plus 0.012. Every year, the population, we assume, is being multiplied by this growth factor, and that happens 50 separate times. So we have 50 separate copies of 1.012 all being multiplied together. The result of that multiplication, rounded to 4 decimal places, is 1.8156. In other words, 1 plus 0.8156, and that means an 81.56% increase over that 50-year period. Okay, that's just taking the growth part of this the new growth part of this growth factor and translating it into the percentage form. Had this been a quantity of money increasing by 1.2% each year, we would have done exactly the same computation. The fact that its population increasing by a certain percent every year does not change the mathematics. What about a population decrease, again by 1.2% each year, and again going on for 50 years? Well, you might think that if 81.56% is how much the population would increase at 1.2% a year for 50 years, you might think that you can just take that percent and use that as the answer to the question about population decline. But that would be mistaken. Let's work through it. So first let's find the decline factor. That's 1 minus 0.012. So every year you're taking 1 minus 0.012, and you're raising that to the 50th power, because every year you multiply by this 1-year growth factor, and there are 50 separate such multiplications. So that's 0.988 raised to the 50th power. This overall decline factor turns out to equal 0.5468. That's for the full 50 years. Just as in the tuition example from earlier, we have to be careful to understand that this 0.5468, or 54.68%, does not mean the population will have decreased by 54.68%, but rather that the remaining population will be only 54.68% of the original. That means that we have to compute, as we did earlier, that the growth factor equals 1 plus the change. Any growth or decline factor has this interpretation. It's always 1 plus the change, and that change is indeed going to turn out to be negative, which is how we know that it's a decline. So we find how great that change is by subtracting 1 from both sides, and sure enough we find that the change in decimal form is negative 0.4532. In other words, there has been a decline of 45.32%. That is how much the population will have decreased. So the math is exactly the same in these population examples as it was earlier in the tuition example. Please go on to the next video.